Thanks for tuning in to my DDL Christmas lecture. I'm going to be talking to you about some of the work we've been doing in the Computational Pharmaceutics Department at Nanopharm, where we've used Bayesian Inference to investigate the behavior of dry powder inhalers. Now, the problem at hand is that we have two dry powder inhaler devices, a test and a reference device, and the test device has been designed to behave equivalently to the reference device. However, as you can see from the three plots on the screen, there's a divergence in their behavior as flow rate increases. Now, for the purposes of this work, we're only focusing on the deposition at stage 4, but the question that we've been trying to answer is, does this divergence as flow rate increases result in these devices being deemed inequivalent by the standard statistical test of bioequivalence that you might perform? And the tool that we've used to answer this question is Bayesian Inference. And here on the screen you can see Bayes' rule. This gives you the probability of a model given some observed data, and you calculate this by taking the likelihood, which is the probability of observing the data given your model, multiply it by the prior, which is the probability of the model before the data was observed, and we calculated that in this case using prior predictive simulations. And this is divided by the marginal probability, which is the probability of the data regardless of your model. And the term on the left-hand side is commonly referred to as the posterior probability, and that is what we calculated when we were doing this. So the model is shown in the box on the right-hand side, and the first term here gives you Yij, and this is the observed mass deposited on stage J for device I. And this value is centered at mu Ij, and mu Ij is the true mass deposited on stage J for device I, ignoring analytical variability, and it's described by a relationship with the flow rate x. And here we use a simple quadratic relationship, which is characterized by three parameters: alpha, beta, and gamma. These parameters are all drawn from multivariate normal distributions, and this allows information to be shared across the relationships for each impactor stage to the covariance matrices capital sigma. And the final couple of terms are the hyperparameters of the model, and these describe the distributions of all of the main parameters. After the model was specified, we then fit it to our data, and here you can see the test data in black and the reference data in blue. Both sets of data fit the model fairly well, and you can see the divergence at higher flow rates quite clearly. The ribbons surrounding the lines and data points are the prediction intervals, and these are what we're interested in for doing further inference using this data set and model. The tool we used to fit the model to the data was STAN, and this separates the model specification into a number of blocks. The one that we're most interested in for the next stage of the work was the generated quantities block. This allows you to take values from the posterior probability distribution and perform further calculations on them. And the results of those calculations have probability distributions associated with those also. Now, we used this to calculate the distributions of confidence intervals surrounding test reference mean ratios that you might calculate in a bioequivalence determination. And this allowed us to predict the probability of success of bioequivalence determinations as a function of flow rate. So the means of these confidence interval determinations seem to suggest that bioequivalence can be determined up to around 70 liters per minute. However, because we have probability distributions on these values, we can also overlay their prediction intervals. And these seem to show that even as low as 60 liters per minute, there is some probability that bioinequivalence will be determined between the test and the reference device. And a really nice way of showing this is in a probability of success curve. Now, this shows the probability of determining bioequivalence as a function of flow rate. And as you can see, it's close to 1 at low flow rates, starts to fall at around 50 liters per minute, is acceptable around 60, and really plummets as you head towards 90 liters per minute. And this confirms the suspicions that we had at the start of this work, that the divergence in behavior of the two devices at high flow rates means that at those flow rates there is a high probability that it will be determined that they are bioinequivalent. So to conclude, we used a Bayesian hierarchical model to investigate the performance of two dry powder inhaler devices at different flow rates. We found that at low flow rates there was a near certain chance that the devices would be deemed equivalent. However, as the flow rate increased, the chance of determining bioequivalence between them dropped very rapidly. The next stage in the work is to expand these calculations to a wider range of impactor stages, and also to start to look at impactor stage groupings. We can then gather further data at a wider range of flow rates to try and strengthen the model predictions. Thank you for listening, and have a Merry Christmas.